All right, welcome to part 2 of solving exponential and log equations. Let's take a little reminder here. The properties we're going to use in the definition, one-to-one properties of equality when it comes to exponentials and logs. A to the x equals a to the y if and only if x equals y. Log base a of x equals log base a of y if and only if x equals y. And this is the property we're going to be using next. The inverse properties. If you have a variable inside the exponent, we switch to logarithmic form. Here we go, this is better. If the variable's in the exponent, we switch to logarithmic form to isolate it. If the variable's inside the log, we'll switch to exponential form in order to isolate it. All right, here's some more examples. Problem 3, solve the logarithmic equation algebraically. So you must show work. We're going to approximate the result to 3 decimal places. Log of 5z equals 4. Well, we cannot rewrite 4 as a log necessarily, an easy one with the same base, the base of 10. And we know that base is 10 because the base isn't written. If the base is not written, it's assumed to be 10. It's kind of like a square root, right? We don't write that little 2 in the nook, but we always write cube root and fourth root and fifth root, anything that's not square root. Same thing for logarithms. Because 10 is common, the common log, we don't write the base. Any other base, we have to express it in some form. So if we have log of 5z equals 4, our variable is here inside the argument of the logarithm, so we'll convert to exponential form. 4 is the power I put on 10 in order to get 5z. Simplify the left side. 10 to the fourth is a 1 followed by 4 zeros, so 10,000 equals 5z. We'll divide both sides by 5 and get z equals 2,000. Do not overthink it. If the variable's inside the log, switch to exponential form. If the variable's inside the exponent, switch to logarithmic form. That's why we study these two together constantly. We don't necessarily do roots and radicals, squares and square roots at the same time. We do them separately because there are other operations, but exponentials and logarithms, they're like peanut butter and jelly. They always go together. Or chocolate and peanut butter in my world. All right, natural log of the square root of x minus 3 equals 8. We could do this in many different ways, but keeping the properties of logarithms in mind will make it much easier for you to algebraically simplify logarithms and logarithmic equations, and it'll also be super helpful when it comes to calculus, when it comes to derivatives and antiderivatives and limits and some of those cool things too. So the first thing we're going to do is we're going to simplify the left-hand side. The logarithm, natural log of the square root of x minus 3 is the same as the natural log of x minus 3 to the 1/2 power. And I'm still going to write equals 8 because I don't want to forget that this is an equation. So I write the entire thing, I just rewrite the left-hand side. But remember, the power rule tells us the 1/2 goes in front. 1/2 times the natural log of x minus 3 equals 8. And now we can multiply by 2 to completely isolate the logarithm. So anytime you get a log with a coefficient of 1 with no powers, it's going to be easier to work with later. So that's all we did here is we took care of that square root, and it ends up multiplying the right-hand side by 2. If the natural log of x minus 3 equals 16, then we can rewrite base of the logarithm is e, so base of the exponential is e. The log equals 16, so 16 is the power. E to the 16th equals x minus 3, so let's add 3 to both sides. And when you put this in your calculator, you're thinking there's no way this could be right, but it is. And when you put it in here, to check your answer, you'll find that it's right. It's weird. It's a huge number. 8,886,113.521, right? 3 decimal places. All right. So if we have the natural log of x plus the natural log of x minus 3 equals 1, our first step is going to be using the properties of logarithms again, and we'll take this addition of logarithms to write it into the multiplication of the arguments, right? If you are Adding natural log of x plus the natural log of x minus 3, since they have the same base, that becomes the natural log of x times x minus 3. And x times x minus 3, highlighted here, becomes x squared minus 3x. Again, I write the equals 1 because I like to keep the equation together so I don't forget what it is that I'm doing. Now that we have the natural log of x squared minus 3x equals 1, we can convert it to exponential form, right? Our variable is inside the logarithm, so we have to rewrite it. So e to the first power equals x squared minus 3x. And once I see an x squared, I'm automatically thinking quadratic equation. 0 equals x squared minus 3x minus e to the first. But we don't write the one exponent on the x, so I didn't write the one exponent on the e because it gets redundant after a while. I have no idea what two numbers multiply to be e and add to be 3, so I'm going to use the quadratic formula to find that x equals 3 plus or minus 9 plus 4e over 2. Now what I want you to do is hit pause, not yet, when I tell you. Hit pause and do the quadratic formula and simplify it and make sure you get that same number as me. I left out probably 4 steps right here. From solve the quadratic to we find that, there are 4 or 5 steps going on right there. So make sure you're able to do that. Quadratic formula, you know it, you know how to use it, or you know how to look it up, and then you know how to use it. When I find my values, this is exactly how I typed it into my calculator to get my estimates. Approximating, we have x is 3.729, and x is approximately a negative 0.729. And hopefully I did the right thing. And I did not. Keep in mind, both of these answers cannot possibly be correct. And that's because we cannot have a negative inside the logarithm. So this is not an actual answer. I'm going to cross it out. Oh, I love that. I need to make sure I do that on the notes. The only viable answer is x equals 3.729 because when I put that value, 3.729, in for both of the x's, the inside of the logarithm stays positive. If I were to put a negative 0.729 in for the x in natural log of x, I would get an undefined term. So this is not an actual solution. The negative value does not work in the original statement. However, 3.729 does. We need to make a change to the notes so that you all have access to that. But I guess I'll know who watched the video. All right, moving on. Part D. Log base 3 of x plus 1 plus log base 3 of x equals log base 3 of x plus 4. There's a couple of different things we could do here, and I tried to keep it as simple of an approach as possible. So on the left, I want to combine logarithms to get a single log. The whole isolate the exponential part, isolate the logarithmic part. So I just looked at the two on the left, log base 3 of x plus 1 plus log base 3 of x, and I know that addition of logarithms turns into multiplication of the arguments. So I'll have log base 3 of x plus 1 times x, and x plus 1 times x is x squared plus x. And then I left the right-hand side alone, but I wrote the whole equation so I didn't leave anything behind. Now, that one-to-one property of logs that I started the video with, log base 3 of this equals log base 3 of that, regardless of what this and that are. If they're the log base 3, those are the arguments and they're equal to each other, we can now ignore the logarithms and just look at the x squared plus x equals x plus 4. Quadratic equation, we'll set it equal to 0, so let's subtract x and subtract 4 from both sides to get x squared minus 4 equals 0. I choose to factor. You could also use the square root property. X squared minus 4 equals 0. Factoring it becomes x minus 2 times x plus 2 equals 0. Zero factor property says x minus 2 equals 0 will give us x equals 2. And x plus 2 equals 0 will give us x equals negative 2. However, so I did do it correctly in this problem. The value of x equals negative 2 will make the argument of both of the original logarithms negative. And if the argument of the logarithm is negative, we can't have that. So the only true answer for this one, we cannot use x equals negative 2. we'll keep the answer x equals 2 as the only viable answer. Right? Sometimes it gives us extraneous or extra answers, and that's how you decide. You always take it back to the original. You always check and make sure it's possible. All right, let's do one more. Log base 4 of x plus log base 4 of x minus 15 equals 2. Adding two logarithms turns into multiplication of the same base, turns into multiplication of their arguments. So we'll combine into a single log using the properties. Log base 4 of x squared minus 15x equals 2. Once we have the logarithm isolated, variable inside the argument of the log, we want to convert to exponential form. So 4 to the power of 2 equals x squared minus 15x. Simplify. 4 squared is 16. So if 16 equals x squared minus 15x, again we see a quadratic. So again we'll get it equal to 0 by subtracting 16 from both sides. Two things that multiply to be 16. They're opposite in sign because the 16 is negative. They're different by 15. So I'm thinking 16 and 1. And since the 15 is negative, the bigger number has to be negative. So we have x minus 16 times x plus 1. X minus 16 equals 0, tells us that x equals 16. And x plus 1 equals 0, tells us x equals negative 1. However, right, as we have talked about in the last two problems, only one of these answers is valid for the domain of the logarithm. So the only solution that we have is x equals 16. All right, solving exponential and logarithmic equations. Take it a step at a time. I encourage you to write, combine, rewrite, simplify, all of some of the same words that I did to guide us as we go through, to keep your thoughts ordered as you're going through the process and your practice. That's all for this lecture. Thanks for listening.